Greetings from student at FK10 Microelectronics Engineering. Today, we are going to present to you our mini project about lead and lag compensator, facilitated by Associate Prof. Dr. Sharon Nizam. But before that, let us introduce ourselves first. My name is Andrew Leong, and I'm the team lead and content verifier for this mini project. Next.
Hello, I'm Kelvin Songbangzi from Microelectronic Engineering. I am the PowerPoint editor and the content writer for this project.
Hi, my name is Wan Beng Kit and I am the data analytic and the video editor. For the introduction, we conclude that what is flow plot, why we need flow plot, and what is lead and lag compensator. Flow plot is a graphical representation of the frequency response of a system. It allows the engineer to determine the system gain and phase characteristic. The importance of the flow plot is to help understand the system behavior, assess stability, and make informed design decisions. Flow plot is needed for stability analysis, highlighting the importance in analyzing whether a system is stable or unstable. Unstable systems can exhibit erratic behavior, oscillation, or even catastrophic failure, underscoring the necessity of stability analysis in a control system design. By the way, lead and lag compensator shape frequency response in control system. Lead compensator introduces a phase lead, improving stability and settling time. Lag compensator introduces a phase lag, enhancing the steady-state accuracy. Both are vital for achieving desired system performance. Now, I will pass to Andrew to explain about the coding and the formulas.
Moving on to the next section, which is the formula derivation for lead compensator and lag compensator. We need to use this alpha and tau value to be coded in our Scilab later on. For your information, the first step to construct a lead compensator is to find the phi max, which is the difference between the required phase margin and the current phase margin, plus a safety phase margin of 15 degree. Then we equalize this value with sine inverse of alpha minus 1 over alpha plus 1, and this value we do some mathematics and we will get the alpha terms. Then we have to use this value to substitute inside the omega m formula, and this omega m we can find it using 2 pi gain crossover frequency, because the gain crossover frequency given is in hertz. Next, we will have our lag compensator, and for the lag compensator, it is much about taking info from the graph. But before we take the info from the graph, we need to find the required phase margin plus a safety margin of 5 degree. And using this phi max, we will go to the graph, the initial graph, and find the value of alpha. After that, this value is stored in the Scilab. Okay, now for gain crossover frequency, we will use this value to find the value of tau. And therefore, we have the two equations for lag compensator also. Next, for Scilab coding, this is the coding for the initial transfer function, where we just need to plot the bow plot. And for your information, line 19 and line 20 is useful for us to construct the lag compensator later on. Next, we will have the lead compensator. For the lead compensator, only 3 values required to be keyed in, and then from these 3 values, they will calculate the alpha and tau value and substitute inside the function and cascaded it with the initial transfer function. And the alpha and tau value will be printed out for our record purpose. Next, we will have a lag compensator, and only 2 values are required to key in. But these 2 values, as mentioned just now, we need to find from the initial bow plot. And using these 2 initial values, we will have the value of alpha and value of tau. And this value will be cascaded with the initial transfer function, and therefore we will plot the bow plot for the lag compensator.
So now, thank you Andrew, and let us continue to our case 1. As we can see from our predefined function, all poles and zeros are at the right half plane, And after we put the value of this function into our Scilab coding, we will get a phase margin of 53.987. The gain crossover frequency is 1.302. The gain margin is negative 3.674. And the phase crossover frequency is 0.207, which the stability of this plot is stable. So after that, we will input the phase margin into our predefined Scilab coding, and we get a new phase margin of lead compensator is 86.824. And after we calculated, we get the percentage increase is 60.85%, which is too large from our ideal percentage increase. So for the lag compensator, we also get a new phase margin of 35.068, and the percentage increase is negative 35.0328%, which is inversely from our result from lead compensator. Now let us continue to the case 2. So from the function, we can see all poles and zeros are at left half plane for this time. And then we will input the value into our Scilab, and we get the phase margin is 126.022. The gain crossover frequency is 1.302, and the gain margin is infinity for this case because the phase plot is not intercept with the negative 180 degree, so the phase crossover frequency, we have no phase crossover frequency in this case, and the gain margin will become infinity. And we can say that the stability is unstable for this case. Next, the result of lead compensator is the new phase margin is 122.4, and the calculation result is negative 2.874%. For the lag compensator, the new phase margin is 129.686, and the percentage increase is 2.907, which is almost reached the ideal percentage increase. So now let us continue to case 3. For the case 3, the poles are at left half plane only. So we will get a phase margin of negative 22.815. The gain crossover frequency is 1.302. The gain margin is negative 1.514. And for this case, the phase crossover frequency is very small value, but it still exists. For the stability, we can see from the plot is unstable. So let us see the result of lead compensator. The new phase margin is 22.364, and the percentage increase is 33.489%. For the lag compensator, the new phase margin is negative 25.54, and the percentage increase is negative value, which is negative 11.944%. So next is case 4. For the case 4, the predefined function is same as case 1, but a pole is at the origin. So we can see the result after using Scilab is phase margin is negative 157.185. The gain crossover frequency is 1.302. The gain margin is negative 4.201, and the phase crossover frequency is 0.319. As we can see from the plot, the stability of this system is unstable. So the result of the lead compensator in this case is the new phase margin is negative 240.942. The percentage increase calculated is 53.286%, which is almost same with the case 1, but a bit smaller. So for the lag compensator, the new phase margin is negative 137.338. The percentage increase is 12.627%, which is uh, nearly same with our ideal percentage increase. And now I will pass the floor to my friend Warren Gate.
Thanks, Kelvin. For case 5, the condition is same as case 1, but a pole at the origin. The G5S is the formula we generated. The phase margin from the formula we generated is 68.271, and the gain crossover frequency is 1.354. The phase plot doesn't intersect with the negative 180 degree, same as case 2, so we don't have phase crossover frequency. Therefore, a gain margin is infinity, and this system is so-called an unstable system. We found that the percentage increase is 39.1418, is much greater than the targeted percentage increase, and so this might not our targeted solution. For the lag compensator, the percentage increase is 27.835. It's still not our targeted percentage increases for the system solution. For case 6, it's same as case 1, but at 0 at the origin. The G6S is the formula that we generated, and the phase margin is 46.628. The GCF is 1.288. The gain margin is negative 3.564, and the PCF is a 0.445. And this system is considered an unstable system. Using a lead compensator, we get the percentage increase is negative 40.393%, is considered a decrease or inversely increase in results. And for the lag compensator, the result in percentage increase is negative 41.217. Is also considered an inversely increase or a decrease, and both results are further apart from the targeted solution percentage. For case 6, it's same as case 1, but at 0 at the origin. The G6S is the formula that we generated, and the phase margin is 46.628. The GCF is 1.288. The gain margin is negative 3.564, and the PCF is a 0.445. And this system is considered an unstable system. Using a lead compensator, we get the percentage increase is negative 40.393%, is considered a decrease or inversely increase in results. And for the lag compensator, the result in percentage increase is negative 41.217. Is also considered an inversely increase or a decrease, and both results are further apart from the targeted solution percentage. For case 7, there's a pole with large value at the right hand. For case 7 is the condition of poles with a large value at the left hand plane, 0 with a small value at the right hand plane. For case 7, the condition of the pole with a large value at the left half plane and 0 with a small value at right half plane. In this plot, there is no phase margin because there is no crossover at 0 dB, so this system cannot be cascaded with the function of lead and lag compensator. For case 8, the condition is the 0 with a large value at the right half plane poled with a small value at left half plane. This system pole plot shows that the phase margin is negative 133.315, the GCF is 13.941, gain margin is negative 62.078, the PCF is 0.959, and this system is called as an unstable system. Using the lead compensator, the result of percentage increase is 11.622%, and using the lag compensator, the percentage increase is 10.937. Both results are showing the value near to the targeted percentage increase. So this might be the solution of the project. And now I will pass to my teammate Andrew for his discussion part. Thank you.
Thank you, Vinkit and Calvin, for the case analysis just now. Now we would like to summarize all the cases and analyze what we have. As you can see, case 4 and case 5 provides a very large increase in phase margin, whereas case 6 has a very large decrease in phase margin. For case 2, it only affects a bit on the increase or decrease in the phase margin. And for case 8, we almost get the ideal cases where we just need 10% of improvement in phase margin. Therefore, we would like to study on case 9, which is our own hypothesis. What we do is from case 8, we add a 0 at the origin, and therefore we have this function. Initially, case 8, we have s plus 2 multiplied by s plus 3 multiplied by s plus 7. But instead, for case 9, we remove the 2 and there is a 0 at the origin. After running the Scilab, we found out that the phase margin, gain crossover frequency, gain margin, and also the phase crossover frequency is almost the same as case 8. But for lead compensator, after we running the Scilab, we found out that the new phase margin is 11.897, slightly higher than the case 8, which is what we don't want because it is very far from our ideal cases. Next, when we do about the lag compensator, we found out that it only increases 10.793%, which is slightly lower than the case 8, and it almost reaches to our ideal cases. And therefore, I would like to pass to Calvin to conclude what we have found just now.
Thank you, Andrew. And now let us continue to our last part, which is conclusion. So, having a transfer function with two small values of both at left half plane, 1 0 at the origin, and two large values of zeros at right half planes is the best configuration. With adding a 0 at the origin, it can stabilize the lag compensator's performance. After the new function is cascaded with the lag compensator, we have got the percentage increase is 10.793%, which is almost reached the ideal case of 10% as our target. At the final of this presentation, we would like to invite Doctor to view our report for this project. So Doctor can scan this QR code or using this link to check our report. Thank you.